Now, having spent all this time, we won't really do much with it. We will do exactly one thing with it. And this is the one thing that we needed this Maxwell term to do. It's to describe something called electromagnetic wave. It's the question of what happens if I have a charge that's in space and it's oscillating up and down. If I have that, what kind of effect would this produce in the space around it? And before we had this term, what we could do was kind of limited. So, if I have an electric charge in space, it's going to produce electric field, right? Yes? Sort of radially going upward. And as this moves, the electric field will change. Big deal, nothing surprising. All right, so we had that from Gauss's law. And you could also describe a charge moving up and down as a current. Kind of something analogous to current, right? Current moving up and current moving down. So you could say, oh, that's a current. So based on Ampere's law, we could say that generates magnetic field that's going around the loop like this. And as this moves up and down, current is changing, maybe sinusoidally. That changes the magnetic field, maybe sinusoidally. And you could say even up to this much. You could say that changing magnetic field will now generate electric field. So this is the picture I was looking up just before class. So this is the picture that you could have gotten so far. You could have said with a charge moving up and down, that generates magnetic field going around in a loop like this. And based on this magnetic field changing, you could say that generates this electric field going like this, right? And that would be where we stop. Without Maxwell term, so I have a changing electric field, but without the Maxwell term, the changing electric field doesn't do anything. So we would say, all right, that's where we stop. No more interesting features. All these things go down as 1 over r squared, and end of story. With this term, what changes is that this chain of events continue. And this results in something called radiated field. And these electric fields that are generated this way, they don't go down as 1 over r squared. They go down as 1 over r. So the electric field strength actually, so we'll just stop there because we're going to talk about plane wave where we're going to pretend that they don't change at all. But so this chain of events starting with here now becomes possible because of Maxwell term. Because of Maxwell term, this changing electric field can produce this changing magnetic field, which can now produce this changing electric field, and then this goes on forever. And this is what we refer to as electromagnetic wave. And I think I might have just enough time. I have about 20 minutes to kind of demonstrate that we do have the correct mathematical relationship to suppose that something like this actually happens. So let me set that up. So this is our Maxwell's equation. I'm going to simplify our Maxwell's equation a little bit, but let me start from, so your textbook tries to do it using this integral form of Maxwell's equations. So you can look at the textbook for that. I'm going to use the differential form because it's a lot easier. And when you do any kind of serious proof work, that's what people would use anyway. It's in this lower division class where some students may not have taken multivariable calculus that your textbook is forced to use this integral formulation, but what's more natural to use is it's the derivative formulation. So let me write that down first. So differential form of Maxwell's equation. I will write them down in the same order so that you can draw some kind of relationship between them. Gauss's law says this: the divergence of electric field is equal to the charge density. So, with all this differential form, one thing that you should remember is that they are local. As in, when you describe electric field at a point, so you are dealing with the derivatives at the point, so you are dealing with the charge density at the point. You get this, enclosed charge, enclosed current, all this stuff when you integrate over some volume or integrate over some area. So it's going to be charge density divided by epsilon naught. And divergence of magnetic field corresponding to this is 0 because there's no magnetic charge. And the one corresponding to this is the curl. Curl of magnetic field is, let me write this down including the Maxwell's term. So let me factor out mu naught. It's mu naught times current enclosed will become current density. So let me use the standard symbol J for that. So just as a reminder, the current density J is equal to current divided by area, and I guess the vector thing is in the normal direction. Okay? So that's the current density. Plus, we need this displacement current, except I'm dividing out area anyway. So this is going to be epsilon naught, rate of change of electric field. And I can leave the vector term as it is. I'll talk about divergence and curl. And the last thing is the curl of electric field. Curl of electric field is given by the differential version of this, which means I get rid of the area. So it'll be minus rate of change of magnetic field. So this is the differential form of Maxwell's equations. And because of the prerequisite / co-requisite arrangement for this class, I have to ask, how many people here are not currently taking or have not already taken Math 3C? Okay, so for those of you who have not taken Math 3C, these symbols don't quite mean much. So let me explain this. So the three symbols I need to introduce are these. One is what's called gradient operator. So gradient operator, and I mean operator sounds fancy, but like a derivative is an operator. It's a differential operator. And gradient operator is the derivative in 3 dimensions. So let me just write down the symbol. It's represented by this upside down triangle with a little vector thing on top. It's because it's a vector operator. Let me write down its form in the Cartesian coordinates. In Cartesian coordinates, this is, so it has 3 components, x hat, y hat, z hat. So it has x hat component, y hat component, plus z hat component. And each of these components are the derivative operator, the partial derivative. So component here is derivative with respect to x. Component here is derivative with respect to y. Component here is derivative with respect to z. I guess the one funny thing about operator is that this is not a function. This only becomes meaningful when you act on a function with it. This is like a reminder. I am going to take a derivative of what? Whatever function comes after this. Yeah, so that's something your math class would spend more proper amount of time. I'll just leave that there. So with this gradient operator, your calculus class would define 2 particular types of operation. Or let me write down all 3. So I mean, so you have the gradient. So gradient is the simple one. It's simply this acting on a function. So a gradient of, let's say, you have a scalar function of position x, y, z. So this could be a function of temperature, right? Temperature is scalar. and you can express it as a function of three-dimensional coordinate system. So when you take a gradient, then this is the what's called the gradient of that function, and it gives you a vector quantity. So like when you think about temperature gradient has a sense of how quickly it's changing as a function of distance and in what direction it's changing. Good? So this is the one operation you can define with this. And the other two operations are, I will write it down and I'll tell you that mathematically it's not that complicated from something that you already know. But this is something your Math 3C will spend a lot of time trying to build the intuition for that I don't have time for. So let me first write it down. The two operations that are defined are what's called divergence and curl. It's two particular type of vector operations you can do with this vector operator. Think of it like this is like a scalar multiplication. You are multiplying a vector to a scalar, you get a vector quantity, right? So in both of these, I'm going to multiply a vector with a vector. Divergence is where I get a scalar. Curl is where I get another vector. So divergence, does this all sound familiar? Like with the vector operations? What kind of vector operation did we do where you got a scalar? Dot product, right? Yeah, so that's what divergence is. It's a dot product. It looks like a dot product. I mean, there's a little bit of, it looks like a dot product. So it's the gradient operator, dot product, with some kind of a vector field. So, some kind of vector field. So I didn't write down vector field here, so let me write it down here. A vector field A, for example, would be, it's a functional position, x, y, z, and possibly time. And it'll have components. It'll have x component, it'll have y component, and it'll have z component. Do you know anything that's like this vector field? Any physical quantity that can be expressed as a vector field?
Electric field?
Yeah. Electric field and magnetic fields are examples of vector fields. It's a vector quantity that's a function of position, has three components. So this looks like a dot product between two vectors. And when you write it out, it's exactly what that is. When you write it out, let me write it out in Cartesian coordinates so that you can see that it's nothing scary. This dot product, it becomes this. So it's only the x dot x that doesn't disappear. So when you do this dot product, there's technically like 9 different products, right? Between 3 of these components and 3 of this component. Of those 9, only 3 survive. X dot x, y dot y, and z dot z. The rest go to 0. So you end up with the x derivative of ax plus the y derivative of ay plus the z derivative of az. In the Cartesian coordinate system, all this looks pretty nice. Something that your Math 3C would spend a lot of time going over is how to do this in different coordinate systems, like a cylindrical and spherical. Those look nasty, and I will not deal with that in this class because I don't have the formulas memorized for once. So that's a divergence. Curl is the quantity that gives you a vector thing back. And if you remember, the product that gave you a vector back was cross product, right? And so this is going to look like this. It's going to look like a cross product. It'll look like this vector operator cross product with the other vector. The only thing that you have to be careful with in this is the order of operation. Not in the sense of this versus the other way around. Like A cross delta, this means nothing. Like this is not curl. Because this is one thing you have to watch out for operators. They have to be coming right in front of something that it's acting on. When you swap the order, you get something entirely different. It's still an operator, it doesn't act on anything. So when you write down this curl operation, you have to be careful in keeping that order same. When you write it down, the derivative always has to come before the component. Okay? So this is probably where it's worth. Do people here remember the component representation of cross product? Yes, no? Let me give you a shortcut to memorize it. How many of you have taken Math 3E, linear algebra matrices? Okay, enough of you. When you take, how many here have heard of determinant? I feel like one determinant part of pre-calculus. Like there's a little bit of matrix in the college algebra, and there you talk about determinants, right? Okay, yeah. So this is based on determinant. This is how you can memorize cross product A cross B. And this is really the simplest way to memorize a cross product. You say that A cross B. So A would have, so A has component AX, AY, AZ. And B has component BX, BY, BZ. And this A cross B can be represented this way. The quickest way to write down the component representation is to say this is equal to kind of a fake determinant. Determinant of this made up 3 by 3 matrix that looks kind of odd. It's, you say it's the determinant of this 3 by 3 matrix that looks like the first row is the unit vectors, x hat, y hat, z hat. The second row is the first vector, ax, ay, az. The last third row is the second vector, components of the second vector, bx, by, bz. How many people here remember the shortcut for calculating the determinant of a 3 by 3 matrix? Works only for 3 by 3 matrix, doesn't work for anything else. No? Yeah, well, I'm almost out of time, so let me wrap up this portion. So the first thing you do is you copy over these two columns so that it looks like a column 1, 2, 3, and then you start repeating column 1, 2 again. It's a graphical method, so you need to have this as well. You need these auxiliary figures to help you make the next figure. So you group these terms together this way. So each of your term is going to be product of 3 symbols. And those 3 symbols are formed this way. You go down diagonally. You can go down to the right. That'll give you these 3 groupings. This is the diagonal grouping of 1, 2, 3 groupings. Okay? And with each of these groupings, you associate a positive sign. That's one set of terms you have in the cross product. If you have seen cross product, it looks complicated, right? So these 3 won't be enough. There's 3 more. And those other 3 you get from diagonal going down to the left. So you have, so these are the 3 diagonal groupings going down to the left. And with these terms, you associate a minus sign. So there's going to be a total of 6 terms. It's usually grouped together by their like terms and unit vectors. So let me write them down that way. And yeah, let me write them down that way. And that'll be the starting place for talking about electromagnetic waves when we come back in the lab section to wrap up this discussion. So, so it'll be long, so let me write it down carefully. I'm going to write down a group of two terms for the x, two terms containing the unit vector x hat, and two terms containing unit vector y hat, and another two terms containing unit vector z hat. And I'll just hunt and pack those ones. So I have, so this is x hat. So one of the terms must be ay and bz. That has plus sign with it. So x hat, so plus ay, bz. And let me go looking for, here's x hat. So another term must have az and by with a minus sign in front. Minus az, by. And this is where I'm going to be super careful. I'm always going to write down a before b. It's because I'm looking forward to this, where I need to always write down the derivative before the thing I'm differentiating. I can never swap that order. So, I mean, yeah, so, all right. So y hat, let me go more quickly. az and bx, az, bx, that's the positive sign. Y hat here, ax, bz, that's minus sign. Minus ax, bz. And the last term, ax, by, minus ay, bx. And there is actually a pattern to this, something called the cyclical versus anti-cyclical permutation that you can actually use that to memorize. But this is the quickest way that depends on something that you are supposed to know already. So let me write this down, and we'll wrap up there. So, so the curl is essentially cross product of this vector and this vector. And as I write down, I'm going to refer to that thing that I just built up, so that I can say curl is, all right, the y component of the first, or I'm looking at the x component of the result of the curl first. And for that x component, I look at the y component of first vector. So the derivative with respect to y, and the g component of the second vector. So derivative with respect to, I guess, y of the g component of the a. So a sub g minus g component, derivative with respect to g, of the y component of a function. You see there's a lot of moving parts that you need to keep them separate. You cannot get different components mixed in, because there's 3 different components to keep track of. Y component of the curl would be, all right, g component, so the derivative with respect to g, of x component, so a sub x, the function, minus the derivative with respect to x of the az function. You might begin to notice some similarities, as in each component happens only once in any term. xyz, xzy, yzx, yxg. And you can use that to make sure you didn't make a mistake. The last term is the g component, this one here. So x component of the first vector, so derivative with respect to x of the y component, so of the function ay, minus derivative with respect to y of the x component ax. So this complicated expression is what's called a curl of a vector field. And the reason I need to introduce this is to tell you about how Maxwell's equation says, what Maxwell's equation says about curl of magnetic field or electric field. Good. So I guess that's all we have time for the afternoon session. When we come back for lab, so it's going to be just a 2-hour lecture. And what we'll spend time on that is, one, deriving the wave equation for electromagnetic waves. And we'll look at some properties of electromagnetic wave as much as we have time for. But once again, the only part that you are responsible for in the final exam is really up to the displacement current and the complete representation of Maxwell's equations. The rest are sort of what I want to talk about, but I can not really test you on. I'll be testing you on physics 4C if you take physics 4C here. No? All right, then we'll continue. So this is what we have covered so far. Maxwell's equations, the set of 4 equations, which I keep telling you describes everything we need to know about electricity and magnetism. I guess to tell you the truth, it's everything about electricity and magnetism as long as you are in vacuum. Because we keep using this permittivity of free space and permeability of free space. So once you start talking about something in a linear medium, then that's where you have to do a bunch more stuff. That's upper division material. I'm not going to do that. But this equation describes everything we know about electricity and magnetism in vacuum. And so in the afternoon session, we just I introduced these as the differential form. And I wrote down some stuff for those of you who have not taken Math 3C, so that these new symbols you are seeing makes some sense. This is a vector operator that takes this form. And when you are using it, you use it more or less like a vector. So when you take a dot product, it looks like a dot product. And when you take a cross product, it looks like a cross product with some care in the ordering of the terms. So there was some, and I guess this is really for people who have taken Math 3C or are currently taking it. You can actually see easily, or with not too much difficulty, you can go from here to here. It's actually more difficult to go the other way. That's why I don't bother trying to derive these expressions from this, because it's a little bit too hard. But once you have this as a given, then to go from here to here, all you really need is application of, I always forget these terms. To tell you the truth, I never actually took multivariable calculus properly. I just took upper division electrodynamics, and they counted it as a multivariable calculus in my school. But to go from here to here, it's an application of, I think, a Gauss's theorem. Is Gauss's theorem something you learn in Math 3C? Yes? Yeah. So this is an application of Gauss's theorem. You do a volume integral on both sides. Right-hand side becomes this. And left-hand side simplifies to an area integral by using Gauss's theorem. Right? Same thing with this. And these, you use a Stokes theorem. You do an area integral on both sides. And right-hand side becomes, current enclosed and flux, all that stuff. And the left-hand side becomes this a line integral by application of Stokes theorem. So that's why this form is preferred. It's the simpler form. If you want to prove anything, it's a lot easier to start out with the differential form and then branch out from there. We use the whole semester the integral form because the assumption is that you haven't taken Math 3C. If you are going through the sequence that's recommended for engineering majors, then you should be taking 3C right now as a core requisite. So that's why I feel now a little bit more comfortable to talk about this form, because I think, well, more than half of you have seen notations here. So it's a couple of you who haven't, this is not going to be on the exam anyway. So the reason I'm introducing this form is I want to use this to talk about talk about the electromagnetic wave. So do you guys remember from end of last semester when we were doing physics 4A, what we called the wave equation, like rough form of that? Yes, you remember the phrase, the wave equation. What was the wave equation, just as a qualitative description? Chris?
I want to say that it had like sine or cosine and it had the phase thing.
You are thinking of the solution to the wave equation, right? So if you have a periodic traveling solution, you could write it that way. But wave equation, it's a form of, I don't know if you guys remember this phrase, equation of motion. So it's a particular type of equation. Anybody here remember what type of equation it looked like? No one here? Yeah, I guess many of you probably haven't taken the class where you might have seen it. You would have seen it in Math 3F, the differential equations class. It's a differential equation. So let me write it down here as a reminder. So the wave equation, so we introduced it early, starting with Math 3C, Physics 4A, because you are going to see this equation in every physics class. And it's important in some of the applications. So anyway, so let me write it down. So it describes a wave, which can be a wave, which is going to be a function of position and time. And this position is potentially it's three-dimensionally specified. And this function itself, it can be a vector, and it also can be a scalar. So a scalar wave would be like a sound wave is a scalar, because it's a wave of pressure, and pressure is actually a scalar quantity. It's not. It's like temperature and pressure. It's a scalar quantity. Or this can be vector also. In the case of the electromagnetic wave that we are going to talk about, this will be vector. So if it's a vector, what you have to imagine is we are dealing with the x, y, and z component of wave. So I can just talk about a single component, and if you're dealing with a vector quantity, you can extend it to other components that may be there. So you're dealing with an equation that describes a function which is a representation of wave, and this is the form of the equation. It says let me write it down in 1D, and I will write down the version for 3 dimensions, but we're not going to deal with it. The version for 1D is that double spatial derivative with respect to one direction, let's say x. That's the direction of propagation. That's the direction the wave is moving. Double spatial derivative of the function is equal to 1 over v squared times double time derivative of the same function. This is the wave equation. And this v, the constant for this is written as 1 over v squared for a good reason. The constant that appears here does happen to be actual wave speed. Did all of this begin to look familiar? I know we covered it. Actually, one of the reasons I actually made the Physics 4A exam cumulative, the final exam cumulative. One of the reasons was I was finding some people were getting through the Physics 4A class without bothering to learn a lot about waves. I wanted to make sure that those people didn't get an A. So, but this is something that you are going to see again. It's not something obscure I'm bringing out of nowhere. It's if you take Physics 4C, you are not going to see this specific wave equation, but you do deal with the wave equation, the quantum mechanical wave equation. So the concepts we are discussing now is something that will come up again and again. So I guess while I'm writing that down, since I went through all this trouble to introduce these notations, let me write down the 3-dimensional version. The 3-dimensional version of wave equation looks like this. You have, so this double spatial derivative, it becomes the gradient dotted to itself. So let me write that as, I'll write it down properly. Gradient dotted to itself. So that gives you the double spatial derivative. Or acting on f is equal to 1 over v squared. And time is just time. It's not, I don't have to do anything special with it. So if we are dealing in the 3 dimensions, the only thing that really changes is the this portion of the equation changes to reflect that the wave can be moving in any 3-dimensional direction. You do have to still pick one direction to go, but it's 3-dimensional. So that's the wave equation. And the reason I'm introducing this is because we are going to get an equation that kind of looks like this, starting out from these laws of electricity and magnetism. And I think I did the derivation for you guys last semester. So I did the derivation for wave on a string. As in, we looked at the equation of motion for an outstretched string, and we looked at what the equation of motion for this would look like if I imagine there's some bend in the thing and see what that would look like. And we got some equation that looks like this. And one of the payoff from that was when you are deriving that, when you are going through that equation of motion, and when you derive an expression, I got out of that equation of motion, I got the coefficient that would fit into this portion. And in case of wave on a string, this coefficient ended up being, I guess, mu over t, where mu is the linear mass density, t is tension, and this meant that the wave speed on string was square root of t over mu. I don't know. I'm pretty sure I derived it. Or, you can look at it in the textbook. But, so this would be actually one of the goals of going through this derivation. So, you are analyzing a medium that a wave can be in, and by going through the equation of motion that describes how the motion happens once, some part moves and there's a force on it, that one of the expected result from that is not the equation itself. You kind of have an idea that you are going to get to this. What you really are hoping to get that you didn't know before is what is the velocity? What is the expression for the velocity? So we are going to go through something similar here. We are going to start out with the Maxwell's equation, and we will go through some manipulation of these formulas. We'll plug something into the other with the goal in mind that in the end, we want to get an equation that looks kind of like this. And we'll see what coefficient ends up in this spot, and that'll tell us what the speed of this electromagnetic wave is. I guess for a lot of people, this is like watching a detective story where you already know the ending. So you know what the speed will turn out to be, but this will be the derivation for that speed. So let me introduce a couple simplifications, because the whole 3-dimensional derivation, it's too complicated. I don't want to do it. So I'm going to simplify some things to make sure I can actually go through the derivation without getting stuck. I guess let me write down the very first simplifying step that I'm going to do. So, question? Did I saw a hand? Okay. So the very first simplifying step. Where's my purple pen? The very first simplifying step I'm going to make is, this is what I'm going to say. So to generate this wave, we do have to have a charge somewhere. So there's a charge somewhere in space. And this charge, from what you know, it actually has to be moving up and down. It has to be accelerating up and down in a sort of oscillatory way. And this is the simplifying step I'm going to make. I'm not going to say that I'm anywhere near the charge. So I'm not going to have to deal with a time-varying charge distribution. In fact, I'm going to be very, very far away from charge, way over here, where there's no charge, there's no current. Now, there is this charge here, and it's moving up and down, can be looked at as current. But this is one of the benefits of dealing with this differential form of Maxwell's equation. These are all locally specified quantities. This is a quantity that I calculate at a particular point in space locally. If I can say that at this point in space, there's no charge, then I can make charge density go to 0. If I can say that at this point in space, there's no current, I can say that I can make current to go to 0. Yeah? That makes sense to everyone? Yeah. So this is not a step that I would have done before, because before that would have resulted in something boring. Because, so let me write it down. So I'm looking at in a region of space with density equal to 0 and current density equal to 0. If I do that, then these equations become the divergence of electric field is 0, because in that particular location I'm looking, there's no charge. The divergence of magnetic field was always 0. And the curl of magnetic field now is a little bit simpler. The first term is 0, but I have to have electric field. If I say electric field is also 0, then that means I'm very, very far away from any charge. Nothing's actually happening. So I'm just going to have the electric field term. So epsilon, I want mu naught first. Mu naught, epsilon naught, and the time derivative of the electric field. Oh, I think I've been a little bit sloppy. Let me correct my sloppiness from earlier. I should have said that this is a partial derivative with respect to time. And what it really means is that, so for this variation, I'm only concerned with how electric field is changing as a function of time. Now, if there's something else that's changing, like a position of charge, then I'm going to ignore that kind of time dependence. All I'm looking for is the explicit time dependence. So with the correction, this should actually be the time derivative, partial derivative in time. It's a fine correction. It's not something that we would have paid all that much attention to in the first place. All right, so the curl of electric field looks like the time derivative minus time derivative of the magnetic field. So this is the simplified Maxwell's equation in, I guess, actual vacuum, where there's no charge, there's no nothing. And before I wouldn't have done this, because before even the third term would have been 0, and it would have been just so much easier to say, well, everything is 0. This is also, B is 0, so this is 0. But once we have these two terms, they can play off of each other and give us something that's non-trivial and meaningful. So this is the very first simplification I'm doing. That just to say that whatever oscillating charge that I have, whatever oscillating charge is relatively far away, so that at this point in space where I'm analyzing Maxwell's equations, I can say my charge density is 0 at this point in space. Let me make a couple more simplifications. So it comes down to, I don't really want to deal with the whole three-dimensional thing, because that requires me to have remembered the triple product and bunch of stuff that I frankly forget. Unless I review it, I'm not going to remember it. So I just want to deal with as a few dimensions as possible. So let's see, what can I say? I think, let me set up my coordinate system first. So I guess I'll keep it to that system here. Let's say my x direction goes this way, and my y direction goes this way, and my z direction goes this way. X, Y, Z, yeah. All right, so I do want to look at a charge that's potentially moving up and down. Or I do want to consider something that's physically real, that's producing wave. But let me say I'm going to only deal with what's called a plane wave. So what's called a plane wave. It's a wave where the wavefront looks like a plane. So not airplane, but geometric plane. So what would be meant by wavefront is, so you know what a wave looks like, right? I don't have a good thing to illustrate wave with. So let me do it with this one. So you know what, roughly speaking, wave looks like. So I'm talking to people who have an idea of shape of wave. So if you have something that's periodic, then you can look at something like this, right? And wave plane would be a plane of points over a particular point on the wave. So like that peak here, that would be a point that you can use to define wave front. And so, so this is a one-dimensional wave. So it really has only one point. But imagine this oscillating, sort of extended. So you'll have to imagine this oscillating is extended all along the horizontal plane. So imagine a series of these linkers here, 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 and at each of the points in space, you can identify a slinky that has some displacement. And imagine this extended in layers along the vertical direction also. So in that case, I can take a point that looks like this bump and have a plane that connects all the points that have the same displacement. That would be the plane that's defining the wave front. And in general, it's not actually a plane. So if you have a source of wave that's maybe moving in circle like this, then this would generate waves that are kind of going out in spheres. But here I'm saying I'm so far away from this source that when I look at those wave fronts, I can approximate them as a plane. Mathematically, this is what it means. So if I'm dealing with a plane wave, then let's say I'm going to deal with electric fields. So I will eventually write down something that describes electric field. If I say I'm going to be dealing with the plane waves, so this is what it means. I pick a direction of wave propagation. So here, let's say wave is going in the x direction. Then by saying plane wave, I'm saying my electric field is only a function of x. It's not a function of y or z. Because as you move along y, your electric field shouldn't change if your wavefront is going to represent a plane. So what this also means is, the x component is a function of x alone, y component is function of x alone, plus the z component is function of x alone. Good? All right, so this will help me simplify some of these equations. You will see how it simplifies once I actually write them down. Write it out in the component form with the help of these expressions for divergence and curl. So let me do that. I think that's the simplest way to show why I'm making this assumption and why that helps me. So take this electric field, for the Gauss's law, for example. So writing out the divergence like this, or it looks like a dot product. It says the x component of this plus y plus z is equal to 0. Right? But when you look at it carefully and keep this in mind, you should realize that the second and the third term immediately go to 0. Yes? Right? Oh, G is, well, it doesn't depend on G. The Y component, it doesn't depend on Y. So these are immediately 0. And that gives you one more result, that this component is equal to 0. So my electric field has no x component that depends on x. So if I have this, well, so my x component is, if anything, it's simply going to be a constant. All right, that's fun. So I think I can actually say this. I can say, for the part that I really care about, the time-varying component, or some component that's going to change as a function of position and/or time, I can say, well, this has nothing that's interesting to me. So I can say my electric field does not have a component that's waving, that's going to be position or time varying. So this is actually something that, this is a non-trivial result to right away, because this is telling us all this thing that I have been pointing out. What this is telling us is that what we are looking at is an example of transverse wave. Everyone here remembers the phrase transverse wave versus longitudinal wave? So, it's a vocabulary word. If you forgot it, go back and review it. This is what transverse and longitudinal means. This is the longitudinal wave, where the oscillation of the wave is along the direction of propagation. That's longitudinal. And transverse means the other thing, where the oscillation is perpendicular to the direction of travel. So because this is saying that any interesting variation is not in the x component, it's in the y and z component, it tells you that whatever wave you get, it's going to be transverse wave. Okay?
What was the other one you said?
Longitudinal. Yeah. All right, so that's interesting. So I think once question?
If it was the x component, not y and z, it would be
If I had a non-zero x component, or x component that's not constant, if this wasn't 0, then it could be a longitudinal wave. Yeah. Yep. All right. So having narrowed down the components of electric field to simply y and z, I think I want to go one step further. I want to be able to say, well, or let me say it this way. It's going to make my next calculation simpler if I had only one of those two components. So this is what it really comes down to. So so far, I've tried to keep things general, other than I'm very, very far away from this oscillating charge, so that I can say it's a plane wave. And with that alone, I got the fact that the x component of electric field is not really changing. Now, I actually have 2 more degrees of freedom remaining if I'm keeping things general. This charge can be oscillating up and down, or it can be oscillating horizontal this way. And apparently what we are getting is that if it's oscillating this way, then we are not getting any wave along this direction. So it can be oscillating up and down, or it can be oscillating this way. I'm going to pick, without loss of generality, the one particular direction. That's going to make the rest of my calculus easier. Okay? So I'll pick up and down direction. So that would be the y direction. So what I'm going to say is that there's no interesting oscillation in the g component simply by my choice of the source oscillating in the y direction. Okay, so I will say this will be 0 by choice. So I'm only going to deal with electric field which has component in the y direction. And that'll enormously help me in going through some of the calculus now. So I guess, where should I start? I guess I could start out with 2 places I can start. Let me start from trying to get an expression that's going to be on the way to looking like a wave equation. Right? What is the biggest difference you see between the wave equation here and the Maxwell's equations here, which is also differential equation? But there's really one way in which Maxwell's equation is nothing like the wave equation here. Yes? Yeah, order. This is second order, right? This is first order. So you know, this taken just as it is, one will not become the wave equation. So what I have to do is I have to increase the order here. So you know, you think of some way to do it, and I'll just tell you what to do because I've reviewed the derivation sometime last semester. So the way you can modify this equation so that it becomes more similar to the wave equation is, so the first 2 equations doesn't really do me any good. So I'm going to do something to the third and fourth equation. And so, you know, it comes down to I want to take a derivative. But, you know, what kind of derivative, right? And what I'm noticing is that I have a formula for the curl of each of these fields. So if I were to take the curl of both sides, then you know I would have to deal with the left-hand side. There's no going around that. But on the right-hand side, I would have minus. You can swap the order of derivatives, right? That's something you learn in calculus class. You can swap the order of derivatives for well-behaved functions, which is always the function we deal with in physics. So you can swap the order of the time and the position derivative. So you have time derivative of curl of magnetic field. Hey, I know what curl of magnetic field is. Here it is. So I can now just plug that in. So that's what I'm going to do here. I'm going to take this expression here, and so I take the curl. Right-hand side will give me something I want that I know how to deal with using this expression here. And left-hand side, I'll just need to work it out. So let me write that down here. So left-hand side, I'll keep it simple for now, or let me write it down here. So let me keep the left-hand side simple for now. It's going to be this, curl of electric field. And we'll work out later what that should look like. That's going to be equal to the right-hand side minus the time derivative of the curl of magnetic field. And this is where I look at this and plug in this for curl of magnetic field. Good? So Seungmin, what do you get when we do that? Well, tell me all the terms. So I have the time derivative. So tell me the right-hand side. With everything that doesn't depend on time, pulled out as far front as possible. Magnetic field will depend on time. So all the time derivatives eventually apply on the magnetic field. So you know what you're essentially doing is you're taking this and plugging this in here. Tell me all the constant terms I get first. I didn't think this was a difficult question. There's 3 factors that are constant. If you see only 2, you are forgetting 1. Well, tell me the factors you see, constant factors. Okay, mu naught, epsilon naught, they are constant. Which is the factor that I'm implying that you are forgetting? No, so, okay, I have this, which will remain inside this. So that's not constant, so let me write that down. So the time derivative of this, so the time derivative of the electric field, which is fine. There's one term that's missing here. This expression as written is not the correct right-hand side. I mean, I won't say it's easy, but it's not super difficult either. No one sees it? This is more of an algebra problem than calculus problem. Pedro, do you see it? Which factor is missing here? Yeah, the negative symbol is meaningful. You can't simply get rid of it. The minus sign remains. There was nothing negative here that would have canceled that out. So I need a minus sign. So you don't actually get the velocity of the wave right away. Because if you are looking at this is a negative coefficient, and you are expecting a positive coefficient. So what you are hoping is that when you go through calculus, when you do the left-hand side, you will also get a negative sign. So those two will cancel out, and in the end, give you something that will resemble the wave equation. So that's why you need to follow. It's not, if this was trivial, I would just, I don't know, I wouldn't bother doing it. It does take, I mean, you could call it tedious, but it does take a fair amount of actual math. It's not, yeah, it does take a fair amount of actual math. So let's see, the right-hand side looks pretty simple. I can just write it down one more step and say that this is the double time derivative, because that's what it is. And then I'm almost there. The right-hand side looks almost like what I want to see here. And all I need to make sure is that, excuse me, the left-hand side ends up looking similar to that. And that's going to take work, because I copied down curl here. Curl is it's not a simple quantity. It is a complicated quantity. So let's start writing it down and see what we get. So let me do it this way. I'm going to say, to start me off, curl of electric field is equal to, and I'll leave the outer layer alone, and I'll do the inner layer first. And as I'm doing the inner layer, what I'm going to do is any term that I recognize from the get-go as 0, I'm not going to write it down. I'll just say that it's 0 and then move on. So this is going to be the result of curl will be a result with 3 vector components. It'll have x component, and y component, and z component. Some of them might end up being 0, but it can potentially have those 3 components. So let's look at that. So these are the facts that I'll keep in mind. My E has no x, no time, no. Wait, can I say that E of x? Yeah, because so for all these, I said to start out with, because it's a plane wave, it's only going to have x dependence. Along the y or z direction, it's going to be constant. So having narrowed that first, from the divergence of electric field, I could say in addition that the x component was constant. So anytime I take any kind of derivative of the x component, it's just going to be 0. And my y component is only a function of x, once again by making it a plane wave. And my z component, I chose that to be 0. to make my calculation simpler. So this is something I'm going to keep in mind constantly, because that's going to simplify this work here. So here, I'm taking the derivative of the g component. OK, that's 0. I said by choice, g component is 0. And then I'm going to take the derivative of the y component, which is not 0, but with respect to z. Well, that's going to be 0, because y component only depends on x. So that's why I've made these simplifying choices, because it'll make potentially complicated vector quantity simpler. And all these are all reasonable assumptions. It's not some crazy special case that I'm bringing in. So all right, x component is taken care of. Y component. So it's x component, so that's 0 from the get-go. Z component, well, that's also 0, because we said that's 0. So all right, that's y component is 0 as well. So I have z component to worry about. Once again, all this is important. We need to go through in. OK, so the y component, derivative with respect to x. Now, that's not going to be 0. So that I need to write down. Derivative of the y component with respect to x. All right. And then derivative of the x component. OK, that's going to be 0 again. So the only surviving term is this term that I wrote down here that ends up as the z component of the resulting thing. So let me just write it down. Well, I guess I can actually leave it here. And I'm going to take another curl, and let's see what we get. We get another curl of this. So when I do that, I'm going to have x component plus y component plus z component. And once again, we go through this exercise carefully, because whenever you are dealing with this gradient operator, you are dealing with the things that have components with other things that have components. That's why you have to slow down and make sure you're not mixing up components of one thing with the other. So as I take this curl, this time you have to remember I'm taking curl of this vector. I'm not taking curl of my electric field vector. I'm taking curl of this vector. So some things to know about this vector. It has 0 x and y component. It has a non-zero z component. That's actually now different. And this still depends only on x. So let's look at this. Then the x component, it's taking derivative g. OK, that's not 0, but with respect to y. That's 0. All right, minus derivative of the y component, that's 0. So the x component, again, ends up being 0, thanks to our, actually, I think x component would have been 0 no matter what. So the y component is the derivative of the x component, which is 0, so 0. And then derivative minus derivative of the g component, okay, which is not 0, with respect to x, which is again not 0. So I actually have to write that down. So it's going to be minus the x derivative of this. So that's the minus double x derivative of the y component of electric field. So you see that we are getting what we are hoping for. We are going to end up with a minus sign. That's going to cancel this other minus sign that we've been worried about. OK, let's finish this up. The z component will be, oh, wait, did I finish this? Yes, I finished it. Z component will be derivative of the y component. That's a 0. So 0. And then minus derivative of the x component, which is again 0. So the z component ends up as 0 as well. And I remember now, this is why I started making this a simplifying choice, because it made this step a lot easier. Before, when I didn't make this choice, I would have some terms written down here and here that I had to deal with, and I didn't want to deal with them anymore. So So that's the result. With this simplifying kind of a one-dimensional plane wave situation, this left-hand side ends up being minus, or y hat. So it only has y component, minus double position derivative of Ey. That's going to equal to the right-hand side. So right-hand side is equal to minus mu naught, epsilon naught. And then let me write out this, this electric field. We started out by assuming that this electric field only had y component, right? So let me write that down. Y component, Ey, or I guess double time derivative of the Ey. And this is one place where we see something that's reassuring, because the reassuring thing is that it's the same component, y hat and y hat. If these had been different components, then we would be in trouble. Like if this is somehow we ended up with, then we would have to say, well, the only way to satisfy that equation is to say the whole thing is 0. Because something that's in the y hat direction cannot equal something that's in the z hat direction. So the only way this left-hand side can equal the right-hand side if these two vectors are pointing in the same direction. And they do. They both the same in the point in the y direction. And what you have is the wave equation in terms of the component. The y component on the left-hand side and the y component on the right-hand side. So minus signs cancel as we wanted. And this is the wave equation that we end up with. The one-dimensional, the plane wave equation that you end up with is the double position derivative of the y component of electric field is equal to mu naught epsilon naught times double time derivative of the y component. And so this is the kind of derivation that Maxwell went through. And this is when he realized that, well, or rather, this is his prediction of something that he would recognize as electromagnetic wave. This is a wave formed by electric field. Nothing but an electric field. It's an oscillating electric field. So what it's saying is that when I have a charge that's oscillating up and down, that causes a ripple in space. And what that ripple is made up of is just the electric field. It's not a ripple of some movement of, it's not a ripple of movement of some physical object. It's not a ripple of movement of air molecules. The only thing that's rippling in this ripple is the electric field. And, or, if we did a similar derivation, except we did it with a magnetic field, then it would be a ripple of magnetic field. And I will tell you this much without going into it too much, that it's a kind of ripple that people haven't seen before. Because when people dealt with a wave, usually there was some kind of a medium. There was something physical that you could point to, water, air, some kind of string, that this is the thing that's doing shaking. But this is the first case where the only thing that you can point to and say, this is what's shaking, is the electric field. And if you think all the way back to the humble beginning of electric field as this device here, you would think that, well, electric field, that's nothing physical. It's just a mathematical device that tells you how to calculate the electric force. And what I have to tell you is that this equation is what gives physical existence to electric field. As in, with this, we can no longer say electric field is a mathematical convenience, mathematical device. It's something that has to physically exist. And what I like to say is that anything that can kill me is not, it has to be real. It's not phantom or something that's virtual. And electromagnetic waves can kill you. what's called the gamma ray. It's an example of ionizing radiation. Is electromagnetic radiation. It can kill you. So it's not oscillation of some faraway charge that kills you. It's the electromagnetic wave that hits you that's gonna kill you, unless it turns you into Hulk. So this is really what gives the strongest argument to the claim that physicists will make, that electric field has a physical reality. So this is the electromagnetic wave, and I guess most of you know this final answer is what is the speed of electromagnetic wave? As in, this is the coefficient that we identify in the location of 1 over v squared. So I can solve for this 1 over v squared and say velocity of electromagnetic wave is equal to this thing reciprocal square rooted. So square root of 1 over mu naught epsilon naught. Can someone tell the class what this is expected to be? Chris? Yeah, this is supposed to be speed of light. And for Maxwell, this was actually a very significant discovery because in Maxwell's time, speed of light was actually known. People didn't know what it was. They were actually arguing over nature of light. Is it a particle? Is it a wave? Newton was the guy who had a corpuscular theory of light. He thought light was particle. And this was actually a debate that was going on in the early 19th century. Maxwell only came up with all this in the 1860-something, 1865. So by the time Maxwell did all of this, people have been arguing over what light was. Some people are saying it was particle, some people are saying it was wave. And actually the wave theorists have been winning for a while because they were predicting all these interference effects. And without understanding what kind of wave light was, they were seeing those interference effects. So people had an idea that light was some kind of wave. They didn't know what. So this, when Maxwell calculated this number, and he knew constant epsilon naught from magnetism experiments. He knew constant mu naught from, epsilon naught from electricity experiment, mu naught from the magnetism experiment. So plug in these two, apparently two disparate, unrelated numbers. Then he gets a number that he recognizes as speed of light, or approximately equal to 3 times 10 to the 8 meters per second. And there's nothing else that's that fast. So when he calculated the number, he recognized that as the number that was already measured from astronomy, where people were measuring the time delay in the Galilean moons from appearing, depending on the distance between Earth and Jupiter or Earth and Saturn, whichever it is. They were noticing that those moons were appearing a few minutes later than they should have. And so based on that, people already calculated the speed of light. And Maxwell was finding this number that he calculates from this theory matches that experimentally measured value of light. So he makes that guess that light is in fact electromagnetic wave. And it won't get confirmed for a while. There are other guys who actually did experiments to generate electromagnetic waves. And I think those might have been done after Maxwell died. And to confirm that the visible light is actually electromagnetic wave would take a longer time. But this is the biggest discovery, that something as familiar as light is actually, comes from this. It's no one would have guessed that light had a kind of electric nature to it before all of this math.